Welcome, high school teachers. This is our final module for the course, and today we're going to talk about some projects and challenges for you to tackle some of the ideas of this course, and also gives us a chance to move in some interesting directions. So our first project is a very simple one, and that will appeal to your students as well, which is simply to make a balance. So here, for example, is a very simple kind of idea that very easy to make. Just a pencil with a couple of clips, balancing here, hopefully, if I put it in the center. And you could maybe attach some paper cups or something there and balance things. And then you could illustrate Archimedes' Law of the lever by moving these things inwards, for example, over here, some appropriate place, and then still having balance. All right. So that's your first project, make a balance, and show us the results of your handiwork. For the second project, we're going to look at the centroid of a triangle, which we've already talked about, but I want to introduce sort of two different ways of looking at the centroid of a triangle. All right, so a centroid of a triangle is obtained when we look at three equal masses. So we have mass M1, M2, M3 at positions A1, A2, and A3, and we're looking at the situation where they're all equal. In this case, the point of balance is the intersection of the medians of the triangle. We could call that the vertex center of mass, because all of the mass is at the vertex of the triangle. Here's another way of thinking about the centroid in terms of a triangle which is a uniform mass distribution. So we're thinking of a triangle that's maybe cut out of a piece of wood. And where does it balance? Well, it turns out, perhaps a little bit surprisingly, that the vertex center and this uniform center of mass are the same point, still the classical centroid of the triangle. And we can see that by the following reasoning, which is very much in the line of the way Archimedes thought. He would have said, well, just think about splitting this triangle up into a lot of thin pieces, say all parallel to this particular side. So if we look at any one of these little thin strips, all right, then this median is going to bisect all of those strips because of a lot of similar triangles. So the point where such a strip meets the median is going to be a point of balance of that little strip. So that means that all these green strips are going to be balancing along that particular median. In other words, that median is a line of balance of the triangle. And so therefore, the same is true for the other three medians. So the centroid there that we found earlier is indeed the point of balance of the entire triangle. All right, so what's your project? Is to make a triangle out of some maybe cardboard or stiff paper, or perhaps out of wood, and just demonstrate that this is actually physically true, that the centroid that you find by looking at the intersection of the medians is in fact the point of balance of the triangle. All right, so for our third project, we're going to have a look first of all at this interesting idea of combining centers of mass by subdividing a given configuration into two subgroups. Okay, so the situation is illustrated by this example. We have 5 masses in the plane. M1 here, M2 here, M3 here, M4 here, M5 here. And each one of those masses is at a position which is denoted by the position vector. So this vector V1 from the origin to M1 represents the position of M1. I haven't shown you the other vectors, but there as well. Suppose we're interested in the center of mass of this configuration, but for some reason we'd like to group these three together, and we'd like to group these two masses together. So these three masses together will have a center of mass, which might be right there, position vector C1. These two masses together will have a center of mass which is somewhere along the line joining them, perhaps right there. That's given by this vector C2. I want to show you that the center of mass of the entire configuration is actually on the line joining the center of mass of this group with the center mass of this group. So it's along this line right here. In fact, it's at a very special point on that segment. All right, so let's look at things algebraically. C1, here's our basic formula for a center of mass. It's 1 over m1 plus m2 plus m3 times the combination m1v1 plus m2v2 plus m3v3 in terms of the three masses and the three vectors. Similarly, the center of mass of the second group has vector C2, which is 1 over m4 plus m5 times the total moment m4v4 plus m5v5. And now let's have a look at the center of mass of the entire configuration. So if capital M is the sum of all 5 masses, then we can write it as 1 over capital M times the big moment m1v1 plus m2v2 all the way up to m5v5. And now we just observe that we can rewrite this thing in terms of these two in a pretty simple way. So if we take the first 3 terms and peel them off, we can see we can write that as this thing here, C1, times m1 over m, where m1 is the sum of the first 3 masses. And then the last 2 terms here with the 1 over m, we can rewrite that in terms of this thing as m2 over m times C2, where m2 is the sum of m4 and m5. So just a little bit of algebra shows that, yes, the center of mass of the entire configuration is a combination of the centers of mass of the 2 subgroups. But it's not just any old combination, it's a convex linear combination because the sum of these 2 coefficients is 1, because m1 plus m2 equals m, telling us that the center of mass of the entire configuration is on the segment between C1 and C2. In fact, it's exactly the place where you would imagine we would have balancing, according to Archimedes, if we had a total mass of m1 at this point and a total mass of m2 at this point, then the point of balance of those 2 masses would be exactly at this point here, given by that formula there. Yes, so let's use centers of mass, to talk a little bit about the geometry of a quadrilateral. It's a very interesting subject. So here's a quadrilateral, A1, A2, A3, A4. And we're going to talk about the 2 centers of mass. The vertex center of mass, where we're assuming that the quadrilateral has actually no mass at all, except for 4 equal masses at the vertices. And then we're also going to look at the uniform center of mass, where we're just thinking about the quadrilateral as being a uniform piece of wood or something like that with mass equally distributed. Okay, so it turns out that in this situation, in the quadrilateral case, these 2 centers of mass do not coincide as they do for a triangle. So let's have a look at the vertex center of mass first. So how can we get that? Well, using the idea that we were talking about in the previous slide, we can think about finding the center of mass of just this pair of equal masses, which is going to be at the midpoint of the segment. And the center of mass of these 2 is going to be at this midpoint. And so it follows that the center of mass of the 4 masses has to lie on this line joining those 2 midpoints. That's sometimes called a bimedian. But the same argument shows that if we look at the center of mass of this pair, which is that midpoint, and the center of mass of this pair, which is that midpoint, that the whole center of mass has to lie on this bimedian. Therefore, it must be exactly the meet of those 2 bimedians, that point C sub V. That's how we geometrically find the center of mass where we have 4 equal masses in a plane. And now let's think about the uniform center of mass. Suppose we have a uniform mass distribution on this quadrilateral. How are we going to find the center of mass? Well, one idea is to think about splitting it up into 2 triangles. So let's say we consider this diagonal here, which cuts it into 2 triangles. This triangle up here, and this bigger triangle below. What we could do is we could find the center of mass of the triangle. And for that we know that the uniform center and the vertex center are the same. They're both just the classical centroid of that triangle. That's obtained by taking the medians of this triangle, so joining a vertex to the midpoint of the opposite side, which we've already obtained. So we can use these two green medians here to find the centroid there of that top triangle. Then we can use these two medians, this one here and this one here, which meet at that point, to get the centroid of that bottom triangle. And then the center of mass of the whole thing must be somewhere between this center of mass and this center of mass. In other words, somewhere along this segment here in red. And then exactly the same argument where we use the other diagonal and we find the other center of mass of this triangle here and the center of mass of this triangle here and join them up. Same argument shows that the center of mass of the quadrilateral must lie on that segment as well, and so it must be the meet of these two segments which join centroids of sort of opposite triangles. All right, so your task is to illustrate this situation with a carefully constructed diagram. So you can do this either pictorially or with GeoGebra. And what I'd particularly like you to see is that once you have constructed C sub u, the uniform center, and C sub v, the vertex center, that the 3 points C sub u, C sub v, and D are collinear, where D is the meet of the two diagonals. So in fact, these 3 points here are collinear on the line. And it turns out, moreover, that there's an interesting ratio between this segment and this segment, which you might like to discover. Our fourth project we might call the book stacking problem. And it's this following question. How many books are required to be stacked successively to the right so that one is completely over the bottom one? So imagine a table here. And these are some books, they're all identical, and we're trying to stack them up, leaning more and more over to the right. The idea being that the top one should eventually be all the way past the bottom one. The question is, how many books do we need? This diagram suggests that perhaps 6 books would work, but maybe we could do it in 5 or 4, or maybe even 3. Let's investigate how this is really going right back to Archimedes' Law of the lever and the idea of balancing. So let's have a look at stacking books. So here is a book. And for simplicity, let's suppose that its length is 2 units. If there's the midpoint there, then this will be 1 unit on this side and 1 unit on this side. And so we can balance that book on top of another book as long as the center of mass of the book, which is at that midpoint, is supported by the book below. All right. So we have to have the book below at least extending as far as the midpoint, and let's go all the way to the limit and put it right at that midpoint, so it's just hovering between balancing and not balancing, but it's just sitting there. All right, and now let's imagine stacking those 2 books on yet a 3rd book and ask ourselves, where could we place that 3rd book so that the 2 books on top of it don't fall over? Well, where is the center of mass of this combined collection of 2 books here? We have one book with center of mass here, the other book with center of mass here. The books are identical, so the center of mass of the configuration is halfway in between, namely right there. Okay, it'll be exactly 1/2 out from that edge. So that's the center of mass of the total 2 books. So we want that supported by the book below it in order to have balance. So if we put that one there, then this configuration will just barely balance. And so the question for you to figure out is just how many books do we have to arrange in some fashion like this so that the top one is actually overhanging completely the bottom one. And an interesting variant of that is to ask, well, suppose that we don't want to go out just one book length, but we want to go out 2 book lengths or 3 book lengths. Is it possible to go out 3 book lengths? Is it possible to go out 10 book lengths? Or is there some natural limit to how far we can go just with a sort of tower of successively stacked books to the right? All right, so here we are with our 5th and final project, which is called Alpha Centauri B. And it concerns our nearest extraterrestrial neighbors. The nearest star to our sun is Alpha Centauri. In fact, there's 2 stars there. They form a binary star system with Alpha Centauri A, slightly bigger, and Alpha Centauri B, slightly smaller. And we're going to talk about how Archimedes' Law of the lever is surprisingly essential to very recent and remarkable discovery that astronomers have made. Namely, that there's a certain wobbling that Alpha Centauri B makes, which is very strong evidence of the existence of a planet around it. And they can show that it's very likely that that planet's mass is reasonably comparable to the mass of our planet Earth. So I want to show you a little bit about what's involved in the general thinking there. So this binary system here, A and B, these are 2 stars which are circling each other. More precisely, they're actually circling their center of mass. They're roughly equal in mass, and so their center of mass is halfway between them. There's actually nothing there at the center of mass. But nevertheless, these 2 planets are revolving in such a way that the ellipses that they make have a focus at this unknown center of mass. So B is going this way, A is going this way, and they go around once like this every 80 years or so. How far are they away? They're about 4.37 light years away from us. This is our nearest neighbor. I remind you that the sun to the Earth is about 8 minutes away as far as light travels. So this is considerably more, yet these are our closest neighbors. Okay, so what astronomers have observed is that Alpha Centauri B is actually wobbling. So while it's going around, it's also wobbling a little bit in this direction. We can only really see the wobble in this direction because we're quite a ways away from it. But with very careful observation of red shifts and blue shifts of light, we can determine that there's a wobble of about 22 kilometers in this position in the direction of the Earth, with a period of around 3.2 days. This is telling the astronomers that, in fact, this planet is rotating around in some kind of circular or almost circular orbit, possibly an elliptic orbit. And what's happening, if we look at it a little bit more carefully, is that here we have Earth way over here, and here is Alpha Centauri B. Actually, it's the center of mass of Alpha Centauri B, the actual center of mass of that big star. And that center of mass is going around in a circle, or pretty close to a circle, which has a radius of 22 kilometers, roughly. And why is it going around in a circle? Well, it's because it's rotating around the center of mass formed by it and some unknown planet that we actually can't see, but whose existence we can deduce from the wobbling. There has to be something on the other side there to generate that motion around this center of mass, just as the presence of this A star here is responsible for the motion of this B star. So Kepler's law tells us that if we know the mass of the star and we know the period of a planet, then we know the distance from the planet to the star. It does not give us information about the mass of the planet. For that, we need to use the actual amount of the wobble, which is this remarkably small amount, 22 kilometers, and Archimedes' Law of the lever. So the story is that the motion of Alpha Centauri's center of mass is moving along perhaps some circle like this. And this unknown planet that we can't see, but which we're deducing, is also going around some larger circle. And there two are kind of going oppositely so that the center of mass is constant there. And what we know is that this radius here is 22 kilometers. And we also know that this distance from Kepler is 6 times 10 to the 6 kilometers, 6 million kilometers. We know that because we know the mass of Alpha Centauri, and Kepler's law allows us to relate the period and the mean distance. The other thing that we know is that Alpha Centauri is pretty well the same size as our Sun in terms of mass. It's about 3 times 10 to the 5th Earth masses. All right. So these are the pieces of information that I want you to put together to deduce how massive is this planet Alpha Centauri B. What must the mass be here so that basically we have an Archimedean balancing situation between the mass of the planet, the mass of the star, and this unknown center of mass about which they're both revolving. All right. So your challenge is to find the mass in Earth units, which is what we're using here, of Alpha Centauri B. And this is the kind of calculation that's really only been possible in the last few years with very great advances in the telescopes and the ability of astronomers to make these various measurements. So it's a remarkable application of a very simple principle going back 2,500 years to Archimedes. So I hope you have fun with the various problems and challenges, and I look forward to you joining us on our next course, which will be on GeoGebra and Bezier curves, where we'll have a chance to explore a little bit more this remarkable dynamic geometry package, and we're going to be applying ideas from this course to describing these remarkable curves introduced by French engineers to design automobiles. I'm Norman Wildberger. Thanks for joining us here at the University of New South Wales.